Okay, welcome back to physics. Uh, Today we're going to be talking about an inclined plane with friction though. Instead of being a frictionless surface, you're just sliding down and accelerating with no friction. Today we're going to talk about what happens when there is kinetic friction involved. Very similar to somebody like you see right here, going down a snow slope. As you go sliding down that slope and having a good time, of course there is friction going on between your skis and the slope right there, which is why a lot of skiers wax up their skis before they go. Oh, we're going to talk about this and we're going to do the same goal, and that is to find the acceleration of our skier going down that incline, but this time with friction. All right, so starting off here, we have our inclined plane. We're going to do a real simple mass one box right here. We've got a 23-degree angle at the bottom of our incline, so it's a nice gentle little slope. And if you remember, the first thing we want to do is, of course, what's the one force acting on that mass right there? And that is your force of weight. Okay, and remember, no matter what the slope is, the force due to gravity always pulls straight on down. So let's draw that nice big vector arrow down like that. And we're going to label that force of weight. And of course, it's a good habit to always write down m times g after that. Okay, now some other information I haven't shared with you yet. We have the mass of object 1. We're going to go with a nice easy number of 100 kilograms. So that's a nice size skier going down the hill. The coefficient of kinetic friction, we're going to skip static friction for now. We're going to say he's already sliding down or she's already sliding down the hill. So our coefficient of static friction is going to be 0.282. And don't forget, coefficient of static friction has no units on the end of it. All right, so continuing on. What are our other vectors? Remember, on an inclined plane, I'm going to kind of go faster on this because we've gone over this a couple times so far, is your force of weight right here is going to break into two components. One of them going straight perpendicular, 90 degrees, right into that inclined surface is your force perpendicular. Okay, and if we draw that right, it should form a nice 90-degree angle right there, making our force of weight the hypotenuse. And then the other force we have to break this up into is the force, the part of the weight that actually pulls our mass down the incline there. Okay, so that one's going to go down this way. And as you already know, that's going to be called force parallel because it's parallel to the inclined plane. Now, from there, let's just draw in our lines. That way we can see our triangles a little bit easier. Makes our sine, cosine, tangent go a little bit faster. And now, remember, these are all similar triangles. So since our big inclined plane's got a 23-degree angle, then that means that this is 23 degrees and this is 23 degrees. Okay? So now we have a couple other players now. Okay? Since we're talking about friction, remember that the force of friction equation, is equal to the coefficient of friction times the normal force. Okay? So that means we have to have two more forces right there. Those two forces have to be identified and labeled on this diagram. So let's add some more forces here. Pick some more colors here maybe. All right. So our force normal, remember normal means that is 90 degrees. And it's 90 degrees to the inclined plane. So that meets the same definition as our force perpendicular. So your force normal doesn't go straight up. It goes 90 degrees to the surface. So it's going to go up that way, right there. So this is going to be your force normal. And remember, force of friction always opposes, always goes in the opposite direction of motion. So since this box, or our mass, our skier, wants to slide down the incline, friction is going to fight you and go in the opposite direction. It's going to go up this way. Okay? So this is going to be my force of friction going that way. All right. So now let's do some calculations here. Using a piece of paper. And we're going to do these sine, cosine, tangents pretty quick because I know you've done these before. So we're going to scoot this over a little bit so you can see it. And we're going to do these calculations over here on the other side really quick. All right, first one we're going to do is our force of weight, because that is our hypotenuse. Force of weight is mass times g. So force of weight, the mass is 100 kilograms times 9.8. So our force of weight is just going to be 980 newtons. Okay? The next thing we need is our force perpendicular. Now that's this triangle right here, and that's the angle of 23 degrees that we know. It's adjacent, and hypotenuse, that's cosine. So the cosine of 23 degrees is going to be equal to the adjacent force perpendicular over the hypotenuse, 980. So that means my force perpendicular is going to be 1,000, rounding up, it's going to be 1,065 newtons. Okay? Now, the next thing we want to do is our force parallel. Our force parallel is this triangle. You know this is 23 degrees, it's opposite, so we're going to have to use sine. So the sine of 23 degrees is the opposite, force parallel over the hypotenuse, 980. So the force parallel is going to be equal to 383 newtons. Okay? Now, a couple of things. First of all, that force perpendicular, which goes straight down here, remember according to Newton's third law, action-reaction. So we got this force perpendicular pushing down into the incline. The opposite force is going to be equal and opposite is the force normal. So in this one, the force normal is not equal and opposite to the weight. No, it is equal and opposite to the force perpendicular. So that means if we look over here at our force perpendicular, that is also going to be equal to the force normal. So the force normal is also going to be 1,065 newtons. Okay? Now, the force of friction, on the other hand, we do not know. Okay? We can't say it's equal and opposite because remember our overall goal here is to find the acceleration. We want to know what the acceleration of our skier or our object is going to be down the incline. So that means this force and this force cannot be balanced. If they are balanced, that just means our skier is going to be sliding down the incline at a constant velocity, no acceleration. But we wanted to see what happens if they're not equal and opposite, and our skier is going to be accelerating down the incline, make life a little bit more exciting. Okay, so that means this force of friction is not, in this case, going to be equal to the force parallel. Okay, we want to see what would happen if they accelerate. So that means we're going to have to calculate the force of friction. And we have that formula right over here. So we're going to rewrite it down here. Force of friction is equal to, I'm sorry, I meant to do that in red. Kind of color coordinate here. The force of friction is equal to the coefficient of kinetic friction times the force normal. So our force of friction is going to be equal to coefficient of friction, which is 0.282 multiplied by the force normal, which we just found right there, 1,065. And when you calculate that out, we find out that our force of friction rounded up is 300 newtons on the button. Okay, 300 newtons. All right. So now what we've done is, remember, we're trying to follow our rules on how to calculate forces. So we have drawn all of our forces, we've labeled all of our forces, and one of the things I forgot to do is we have to assign positive, negative directions. So little symbol up here, our Cartesian system, we're going to say to the right is positive, left is negative, up is positive, down is negative. Okay? So applying that to this, that means my force of friction here is going to be positive, and my force parallel is going to be negative. Okay? Now, my next step, I now have all these components done, and now we need to find out what the acceleration is. And following our steps, we have drawn all of our forces in. We've labeled them all. We've calculated the components everywhere. So now we need to sum up the forces along the line of direction. Okay? So we are going to sum up all of our forces. So let me scoot this paper over a little bit here. Oh, there's my protractor. All right. So we're going to sum up all the forces along the direction of motion, which in this case we'll call this the x, along the inclined plane right here. Okay? So we're going to say x, and that's the only forces going in the x direction right here are your force negative parallel plus the only other force is the force of friction. So now we ask ourselves the question, according to our 7-step process, is this object supposed to accelerate? And we're saying yes, it's supposed to accelerate. If that's true, then we learned on the last lessons, we're going to substitute in Newton's second law. Because if there is a net force, then there's going to be mass times acceleration. All right, let's plug some of these numbers in. Negative force parallel, which is right there, negative 383, plus the force of friction, which we found down here to be 300. And we can also put our mass in now. Remember, our mass over here was 100 kilograms. So this is 100 times the acceleration. Negative 383 plus 300, of course, is just negative 83. And then when you solve for a, you're going to have negative 83 divided by 100. And our acceleration is going to be negative 0.83. And the units are meters per second squared. So there we are. We've just calculated that the acceleration of our skier or our box, whatever we got going on here, down the inclined plane with friction is going to be in the negative direction. Now remember, good physics people, we always go back, see if that makes sense. This thing says it's going to be accelerating in the negative direction. And the negative direction is down the incline. So that is correct. So our skier is going to be accelerating down the incline at almost 1 meter per second squared. So every second that goes by, they're going to gain 0.83 meters per second. So that's a pretty good increase. Our skier should be flying down that hill pretty fast. All right. Thank you for joining in today. I'll talk to you later.